Hello, I'm Steve Miller. Today I'd like to talk about an alternative analytical solution for the planar oblique shockwave problem. I'd like to acknowledge DARPA for supporting this research under the Young Investigator Faculty Award Program. Today I'd like to talk about an introduction and motivation and for the reason we're doing this work. I'll give an overview of previous approaches and talk about a broad overview of the present approach. Then I'll develop the approach for the particular shockwave solution of Prandtl and Meyer. We'll present some predictions and end with a final prediction of a bow shockwave. The DoD has a need to analyze quickly the near field of hypersonic flight vehicles. Unfortunately, present theory cannot predict the near field, which we'll review shortly, which is based on the so-called F-function and impulse method, which are two analytical methods used previously for supersonic flows or bluff body flows hypersonically. Experiments can measure these, but generally hypersonic wind tunnels can't capture high Mach number, high enthalpy, and realistic flow fields in the near field. They can't match all the similarity parameters. CFD can, but of course it's very hard to validate CFD without actual data. So we wish to create a new nonlinear theory to ascertain quickly the near field for sonic boom prediction and analysis of flight vehicles. Here's two example flight vehicles that are motivating examples. One is from a Lockheed Martin European patent on the left, which is a wave rider type concept. On the right is the hypersonic air-breathing weapons concept, the HAWK, from DARPA. And there's no analytical theory that can predict the near fields, unlike F-function impulse method. Generally, there's some aerodynamic body, which would be in gray, and we want to predict on a source cylinder the static pressure around the vehicle. This would then be used within a sonic boom propagation code to predict the noise on the ground. So the input for the sonic boom propagation code would be that middle line of delta P over P versus X over L, and the bottom would be the N wave predicted at the ground. So we're attacking the problem to just use the vehicle geometry, the vector Mach number, and the atmospheric quantity near the vehicle to predict the near field with no other information and no numerics. There's two major theories that are predictive analytically. The first is the F function, and that uses basically cross-sectional areas of your flight vehicle to predict the near-field pressure by Dr. Maslenikova in the Soviet Union, and independently by Gerald Whitham, a applied mathematician at Caltech on the right. Here's the F function itself. It's basically an integration area with respect to X along the flight vehicle, and it works really well for cylinder vehicles, even with lift at supersonic Mach numbers. For say Mach 2.3, it works really well, as seen in the right figure by Carlson from NASA NTRS. But if the Mach number increases to 4.63, things don't work as well. In part C in the lower right, you add lift effects and things break down. Second major approach, which is analytical, is the impulse method, and this is where we might have a long cylinder with an instantaneous impulse of energy. These work well for hypersonic bluff bodies, but cannot have lift. Here's a particular equation from the impulse method, and it can be seen as just a simple algebraic nonlinear equation in closed form for the change in pressure at the ground. It can only predict the overpressure at the ground from an impulse of an infinitely long cylinder with spherical leading edge. This was published by Tiegerman in 1975 in his dissertation. Let's return to where all this started, and I think everybody's familiar from their compressible flow classes in aerospace engineering of the work of Theodore Meyer and his advisor Ludwig Prandtl. These are their pictures, respectively, on the right and left. The theory of shock waves was originally published by Prandtl's student Theodore Meyer in his dissertation. On the left, I screen captured his Ph.D. dissertation. You can see this diagonal line is from a wedge-type flow in 2D, where an oblique planar shock wave radiates from the leading edge or corner in this flow. It was validated within nozzles in Professor Prandtl's lab. It resulted in the famous theta beta Mach number equation. In 2 dimensions, you can solve this for the wave angle beta analytically, but you cannot do that for non-2-dimensional flows, at least to my knowledge. We wish to exactly recapture this solution, let's talk about the overview of the present approach. We wish to recast the Navier-Stokes equations as generalized functions and integrate them about a surface which is moving arbitrarily in space and time. We will write a closed-form solution for the density, which will depend on a convolution integral of something like a Green's function, but this is a nonlinear equation, and the particular source. So we'll just write down the equation and find if we can find in the functions to give a valid solution. The source is only going to be a function of the ambient fluid properties, vector Mach number, and surface shape, and it should only be constructed with the product of generalized functions, in particular a product of Heaviside functions. Here's the governing equations, which are written as generalized functions. The first on the page is the continuity equation, and the right-hand side has a generalized function of delta. And f is an arbitrary shape evolving in space. The second equation is the generalized momentum equation, and it turns out we don't need a gas law to solve for the density field, and we will recover other variables via basic theory once we know the density field. Our goal is to find a closed form solution of these two equations. Write the solution as an integral, a convolution integral of something like a nonlinear Green's function, if something exists like that, with the source function w. W is nothing but a series of terms which represent the solution of the previous two equations. So our major challenge is to find the source term w given some shape, and it should only be a function of the shape f and Mach number, and some kind of propagation equation, which is a nonlinear Green's function. Now, y will be a vector from the vehicle to the position in the near field. And this is what the traditional f function would give us in terms of going from the source surface to the source cylinder. Tau will be the time history of the signal, and t will be the observer time of the signal. Now, the source term can be written as a sum of three terms. The first term will be the volume displacement of the vehicle. This is directly accounted for in the f function or impulse methods. The second term will represent the so-called stress on the vehicle, and it'll represent the lifting components. This is just like the a sub L term in Whitham's theory of the f function also. Finally, there's a term that we're going to neglect for now because we're looking at inviscid flows, and this will represent the effect on the near field from, say, turbulence, and would account from the exhaust plume or wakes. Let's now look at the wedge flow solution. Here we have the arbitrary domain where f is perhaps 1, and inside the surface we'll set it to 0 or less than 1. There'll be a surface which represents the geometry of the vehicle, or in this case the wedge shape, which is moving in space, and our observer will be moving with the surface. If we set up the problem like this and set the surface to be a single wedge, just like Meyer's solution, then we can write down exactly this Heaviside function, which is only a function of the ambient Mach number and the turning angle of the wedge. If we take that Green's function, or nonlinear Green's function, if you will, and convolve it with the source term, which I just showed 2 slides ago, that will be the first term on the bottom of the slide, and we'll multiply it by g wedge. The integration has been done already analytically for us. On the left, we'll have a change in density. So depending on where we are in the field, we'll get the change in density across the shock, and we've recovered analytically the solution of Meyer. On the top are particular examples of turning angle of the wedge for attached shocks with density rise ratio, and it exactly matches analytical solutions for 2D oblique shocks. I'd like to show one more prediction to show the power of the method. On the left, we have a CFD simulation of a spherical leading edge with conic surface moving at Mach 3.5. The half angle of the cone is 7.7 degrees. From this SU2 solution, which is open source CFD from Stanford, we've extracted the static pressure along the white line. On the right, we've plotted the CFD solution as a line with pressure on the y-axis and the axial distance x on the x-axis. And we've used this prediction technique to estimate or predict the static pressure from a convolution of a Green's function with a source definition based only on the geometry and incoming Mach number. As you can see, it matches fairly well. I've created an analytical framework to ascertain the two-dimensional near-field solutions within supersonic and hypersonic flow fields for density and other thermodynamic variables. These match exactly with the analytical solution of the wedge of Meyer. Also, expansion solutions match. We've shown a Bow-Shock solution for a two-dimensional case, which matches with CFD. Thank you very much for your time today, and we look forward to your questions.